Remember at the beginning of this unit, we talked about the Dalton solid sphere model of the atom. Basically just said the atom is a pool ball, or the atom is a marble, where it's a solid sphere. Each of the marbles are a little bit different from one another. Each of the atoms are a little bit different from one another, but they don't consist of anything smaller than the marble itself or the pool ball itself. Okay, the atom is the atom. It's as small as it possibly gets. And then we talked about the Thomson plum pudding or the Thomson raisin bun model of the atom, where Thomson, remember, used the cathode ray tube to discover the electron, and then that raisin bun model of the atom said that the atom consists of a bunch of little negative particles called electrons floating around in a sea of positive charge. And then we took a step aside for a little while and started talking about the nucleus. Now we're going to go back to talking about the models of the atom and develop a third model of the atom. We call it the Rutherford model of the atom, or sometimes we call it the planetary model of the atom. Before we do that, I want to describe the experiment that led to this Rutherford or planetary model of the atom. Rutherford has set up in his lab basically a box that contains a radioactive material that will produce alpha particles. It's not a box of alpha particles. It's a box of radioactive material that will generate, that will decay into alpha particles. And these alpha particles are released through the opening in this box. And they move towards, one at a time, they move towards this really, really thin gold foil barrier. Like we're talking about like aluminum foil type thing, except even thinner. If you've ever seen, you can see these sometimes in the baking section of a grocery store, gold foil. You ever seen this? These tiny little chunks of gold foil. It's actually gold, and you put it on your baking for decoration, and you can actually consume it. You can actually eat it. We're talking about gold foil, really, really, really thin like this, except it's a sheet of gold foil. Now, surrounding this thing, we have this screen that we call a scintillation screen. It's a screen that will glow when struck by the alpha particles. That allows us to see where the alpha particles struck without being actually able to physically see an individual alpha particle. So in other words, if the screen glows right here, we know the alpha particle struck right there. Or if it glows right there, we know the alpha particle struck right there. Now, how does this experiment go? We fire these alpha particles one at a time, although we don't necessarily control how quickly they go because we're not controlling how quickly they're decaying. But they're still going one at a time at this thin, thin, thin gold foil. Rutherford and his assistants, one of his assistants, by the way, his name was Geiger. Where have you heard that name before?
Geiger.
Geiger, G-E-I-G-E-R. What is it? Geiger counter, yeah, same guy. Okay, working with radioactive material here, develops a Geiger counter to count the amount of radioactive decay that's taking place. Rutherford and his assistants, including Geiger, fire these alpha particles, and they find that the vast majority of these alpha particles, they go straight through. Most of these alpha particles go right through, straight through, and strike the scintillation screen directly through on the other side. Now, I'm going to tell you what that means in just a moment. That's where the arrow comes in there, but we'll just hold off on that until we look at all the other observations that were made. Most of them go straight through. Some of these alpha particles go through, but are deflected. Less of them, but quite a few still. Some of them go like this. They get deflected like this. They're still going through, but they're striking the screen somewhere else other than straight through, straight across. Some of the alpha particles went through, but are deflected. Finally, a few of the alpha particles, not very many, but a few of them end up bouncing back. So they hit this gold foil, and then they bounce back and hit the screen here, or they hit the screen here, or they hit the screen here. Now we have to develop a model of the atom that would explain these observations. Before we do that, I want to give you an analogy here to help us through this. Okay, let's say we're out of the football field. On the football field, there's 110 yards. We've got one person on each yard line. Does it make sense? So anybody who's in the United States listening is going to be like, what? Football field's not 110 yards. Yes, a real football field is 110 yards. And we've got a person standing on each yard line, okay? You're all blindfolded. And I guide you. I place you so that you're aiming straight across the football field. You can't see anything, but you're automatically pointing in the right direction because I pointed you in the right direction. And then I just call it a number between 0 and 110, and I say, hey, 27. Who's ever on the 27-yard line is going to walk across the football field, blindfolded. When I call 27, the person on that yard line walks straight across, makes it across to the other side of the football field on the 27-yard line. When I call 85, the person walks straight across the football field. When I call the vast majority of those numbers, the vast majority of those people walk straight across the football field. What does that tell us about the composition of the football field? What does that tell us about what's on the football field? They pass through unobstructed. In other words, the football field is pretty wide open, right? There's not much there. Since the vast majority of people walk straight across the football field, the vast majority of the football field is empty space. The vast majority of the atom is empty space because the vast majority of these alpha particles went straight through. So we're going to say most of the atom of gold, but that can be extended to any atom. Most of the atom is empty space. Some of them went through but were deflected. So I call on 54. Okay, the guy on the 54-yard line walks across and he makes it to the other side of the football field, but he makes it across on the 39-yard line. So somewhere in that process of walking across the football field, his direction changed. Okay, 52, same thing, walks across and ends up on the 49-yard line. 57 walks across, ends up on the 61-yard line. So there's a few of these people, some of these people that end up making it across, but they're deflected. What does that tell us? Well, there was something in there that was pushing these people walking across the football field off of their straight line path, right? What would push a positively charged alpha particle off of its straight line path? No. Something that's positive would push a positively charged alpha particle off of its straight line path. So we know that most of the atom is empty space, but there must be something small and positive. It's got to be small and positive, otherwise it wouldn't push these few alpha particles off of their straight line path. We're going to call it a nucleus, a small positive nucleus. Pushes these alpha particles off of their straight line path. Now, let's say of the 110 people, one person walking across the football field, let's say the person on the 55-yard line at center field here, walking across the football field, ends up not making it across. That person just, at some point, just bounces back, ends up back towards where they came from. What does that tell us? They must have hit something, right? They must have hit something. And that something that they hit must be, let's say that Thomas is running across that football field and he bounces back. He bounces back. Well, Thomas is not going to bounce back if it's a 2-year-old standing in the middle of the football field, right? Thomas is going to run straight through that 2-year-old and make it across to the other side of the football field. So, what do we know about that thing that's in the middle of the football field? That thing that is small and positive? We also know that it is relatively, not big, it's small, but rather heavy or dense, right? It's got to be small, it's got to be positive, it's got to be small because most of the atom is empty space. It's got to be positive because it pushed away some of these alpha particles from their straight line path, and it's got to be heavy or dense. Otherwise, this alpha particle that was going through would have just knocked it out of the way and went straight through or got deflected again. So the fact that these alpha particles bounce back tell us, or a few of these alpha particles bounce back, tell us that that thing that's causing them to bounce back has got to be pretty heavy, relatively speaking, or dense. So now we have this model of the atom where we have a small, dense, positive nucleus. We still don't have protons and neutrons, but we do have a small, dense, positive nucleus. This is a revolution. We went from an atom that consists of a bunch of electrons floating around in a sea of positive charge to an atom that has a nucleus with electrons orbiting around that nucleus. This isn't our current model of the atom, but boy, it sure does look an awful lot like our current model of the atom, right? Where we have a nucleus that takes up only a little bit of space, and then we have electrons orbiting around that nucleus. Let's talk about another model of the atom now. So we went from the Dalton solid sphere model the very first day to the Thomson Raisenbund model the very first day. And now we skipped a few days, did some other stuff, and then we talked about the Rutherford. We call it the gold foil experiment. Sometimes we call it the alpha scattering experiment because that's what we're doing, right? We're scattering alpha particles to devise the planetary model of the atom. Well, next we're going to talk about the Bohr model of the atom. Niels Bohr looked at the Rutherford model of the atom, the planetary model of the atom, and found a lot of good with it. He would have looked at it and said, hey, this guy Rutherford said that there is an atom that consists mostly of empty space. Yeah, okay, that works for me. That works. But there's a small, dense, positive nucleus somewhere in the middle. Yeah, that works for me, he says. There's electrons orbiting around that small, dense, positive nucleus in this mostly empty space atom. Yeah, that works for me. So what separates the Bohr model of the atom from the Rutherford planetary model of the atom? Well, Niels Bohr talked about electron levels. Okay, that's really the one word that differentiates. If you have to pick a word, that would be the one word that differentiates the Bohr model of the atom from the planetary Rutherford model of the atom. Electrons orbit the nucleus, not just anywhere they want, but they orbit on specific levels. The first level, the second level, the third level. In chemistry, you learn that the first level can have 2 electrons, the second level can have 8 electrons, and so on. I don't remember all the numbers. That doesn't matter for us. We just need to know that they orbit around on specific levels. And each level is characterized by a specific amount of energy. You go to a Flames game, okay, there's 3 levels, right? There's the first level, there's the second level, and then there's the third level. The first, and you have to watch the game on a specific level, either the first level, the second level, or the third level. You can't be in both levels at the same time. You can't be anywhere else other than on one of those levels when you watch the game. Now, if you've been to more than one game, you'll also recognize that oftentimes it seems like each level is characterized by a specific amount of energy, okay, by a specific energy. People on the first level tend to be calmer. Those are the business people coming from work, sometimes still dressed in suits, and they tend not to be quite as loud. If you go to the third level, the sport check zone, or the press level, as they call it, then those people tend to be louder. It may be, they may be assisted by something that they've consumed in a lot of cases. Okay, people up there, on average, tend to be a little bit louder and a little bit more energetic, right? And then the second level is kind of that mid-level where it's not quite as loud as the third level, a little bit louder than the first level. So we have to exist, we have to be on a level, and each level is characterized by a specific amount of energy. The second thing that distinguished, again, if we want to pick one word that distinguishes the planetary model from the Bohr model, it's levels, electron levels. And everything else is kind of built around this idea of electron levels. The second thing is an observation. Electrons orbit around the nucleus on specific levels. And as they orbit around on those specific levels, they accelerate. It's a centripetal acceleration, right? Object goes in a circle, it experiences a centripetal acceleration. It accelerates. According to Maxwell, it should generate EMR, but it doesn't. It's as if these electrons aren't accelerating because they're not emitting EMR. We call it a stationary state because it's as if they're stationary. It's as if they're not accelerating. So there's something up with the model here because these electrons should be emitting EMR because they're accelerating. They are not emitting EMR. It's as if they're stationary. And the third aspect of it is that electrons can make transitions. They can make transitions from low levels to high levels. Okay, if you go to the Saddledome and to watch a hockey game and you have tickets in the third deck, you know that you have to make a transition from the first level all the way up to the third level. And in order to do that, in order to make that transition, you better have a lot of energy. You better have consumed energy. You better have absorbed energy because it's a big climb. It's a big climb up there to row 20 in the sport check zone. You better have eaten your Wheaties in the morning or had a Red Bull before you arrived at the rink or something. Because in order to jump to a higher level, you need to absorb energy. But understand that you can also, as an electron on a higher level, if there's a vacancy in a lower level, you can fall down to fill in that vacancy. It's like you're sitting up there for the first period in the sport check zone, and you've been watching these two seats right by the glass this whole time, this whole first period, and nobody sat in them. What do? You move down. You go snag them. You move down to the first level. So as you fall to a lower level, you give out this little shout of glee because you're happy that you just spent $30 on seats and you're now going to sit in $200 seats for free, well, for $30. You're falling to a lower level. As you fall to a lower level, you give off energy. Now, the energy that the electron absorbs to jump to a higher level is usually EMR, although not necessarily. It can absorb essentially any type of energy to jump to a higher level if it receives it, if it's available. But when it gives off energy to fall to a lower level, it's going to give off EMR. Always going to be EMR. A photon, think back to your last unit. What type of EMR would it be? Infrared, visible light, and ultraviolet. Because remember we said that those were produced by transitions of electrons in atoms. That's what we're talking about here now, right? Transitions of electrons from high levels to low levels in atoms. And if it was a really, really big transition, we said that X-rays could be produced there as well, but not usually. Usually it's one of those three types, infrared, visible light, or ultraviolet. All right? Okay, if you flip over the handout that I gave you, you're going to see this diagram. This is the reason that I photocopied the notes here today, just so that you could see this diagram and not have to try to draw it or whatever. I want to draw a line that separates the first diagram from the last two. That first diagram is going to be kind of a reference diagram for us. This doesn't really describe anything involving electron transitions. This is just, look, you got a hot glowing solid, or a hot glowing liquid, or a hot gas under high pressure. It will generate all types of EMR. It'll generate a continuous spectrum, all the types, all the colors of the rainbow. It looks like white light. When that white light goes through a prism or a diffraction grating, either one would work, right? Prism would split it up into Roy G. Biv. Diffraction grating would split it up into Viv G. Orr. But they would both split it up, right? Okay, the prism and the diffraction grating splits it up, and this is what we see. We see the rainbow. Okay? Nothing to do with electron transitions, just a reference diagram so that we can compare it to the next two diagrams. Now, in the second diagram, we'll label this number 1. In the second diagram, we have a hot gas. Notice the difference here under low pressure. Hot gas under high pressure produces a continuous spectrum. Hot gas under low pressure, well, it produces, like if we're standing right here, it looks to be pretty much the same. If you look at the fluorescent lighting above, you're not really going to distinguish the light that's coming off of that from the light that's coming from the light bulb in your house, right? It looks the same. But if you put the light from an incandescent source coming from the lights in your house through a prism or diffraction grating, it will split up and form this. If you put a prism or diffraction grating in front of this, it will split up and form this. This is what we call an emission spectrum. Sometimes we call it a line spectrum. What's the difference? Well, this produces all types of EMR. Hot gas under high pressure produces all types of EMR, everything. But a hot gas under low pressure only produces EMR as a result of transitions of electrons, which means that we're not going to get all types. We're going to get a red type, a red photon given off corresponding to one transition. We'll get a orange photon corresponding to a different transition, a couple greens corresponding to two different transitions. Right here, they look the same because everything's all together. But when we split them up, this one produces a continuous and this one produces a line spectrum or an emission spectrum as a result of specific electron transitions. So hot solid, hot liquid, or hot gas under high pressure, everything, continuous spectrum. But if you have a hot gas under low pressure, it produces this line spectrum that corresponds to specific electron transitions. Now, let's look at diagram 3. Let's take away something from diagram 3 though first. Here we have our light bulb or our hot solid, or it could be a hot liquid, or it could be a hot gas under high pressure. What does it produce? Everything. Looks like white light, right? But when I put it through a prism or diffraction grating, what happens? I get a continuous spectrum, right? I get the first diagram. It is exactly like the first diagram, right? But when I add this cold gas to it, what do you think happens in the meantime? This cold gas absorbs certain photons. It absorbs a red photon. Why is there a black line there? Well, because that red photon was absorbed by the cold gas to cause an electron to jump to a higher level. Why is there something missing right here for blue? Well, because there was a blue photon absorbed by the cold gas causing an electron to jump to a higher level. What do you notice about the second spectrum and the third spectrum? They're the exact opposites. So what do you know about that hot gas versus that cold gas? It's the same gas. A hot gas under low pressure will emit very specific photons of EMR corresponding to very specific transitions. The same cold gas will absorb those photons, causing electrons to make jumps to higher levels, causing the exact opposite spectrum, an absorption spectrum, we call it. This spectrum that we see right here, whether it's emission or absorption, is unique to whatever gas this is. In other words, we can use this spectrum to effectively fingerprint the gas. We can identify the gas based on its spectrum. If we were to, tonight, look out and discover this star that nobody else has ever discovered, it happens. It does happen that even amateurs discover something that professional astronomers have never seen before. If we were to do that, we were to see this star, we want to find what the composition of this star is. Well, we could look at the light that's coming off of this star and put it through essentially a prism or diffraction grating and look at its spectrum. We would get an emission spectrum An emission spectrum, because this hot gas under low pressure would be producing, well, what appears to be white light. When you look up at the sky, it looks white, right? But then when you put it through a prism or diffraction grating, it splits up the colors into this emission spectrum. We could compare that emission spectrum with known spectra to determine what was present, what element or elements were present in that star. Does that make sense? Does that make sense? So hot solid, hot liquid, hot gas under high. Here's the way you remember this, the difference between the high and low pressure. Which one's which? Hot solid, hot liquid, hot gas. Okay, what's the common letter here? H, high pressure, right? Hot liquid, hot solid, hot gas under high pressure produces a continuous spectrum. But if we have a gas under low pressure, hot gas under low pressure, it's going to produce a line emission spectrum because of specific electron transitions. The same gas, cold, will produce an absorption spectrum because it absorbs certain photons. That is, if we have this here. Right? If this isn't here, what do we see? No, nothing. There's no light, right? It's this that generates the light, and then it's this that takes away these photons. So if we just have the cold gas, we're not going to get any absorbed. We're not going to have any light, period. All we're going to see is black. There's no spectrum to see there. And that next diagram is a copy of this. It says 3 known spectra here, hydrogen, helium, and sodium. And we want to know this unknown gas mixture, what it contains. So you just discovered a star. You just discovered a star. And this is the spectrum that's produced by this star. If this was on an exam, it would probably be in color. Okay, so these lines right here would probably be in color. Doesn't matter though. It doesn't really matter. You can see the wavelength of these lines, so you know roughly which is which. We want to compare this unknown gas mixture that we observed from our star that we discovered tonight with these known spectra, hydrogen, helium, and sodium. We want to determine what's present in it. Is hydrogen present in it? Yeah. How do you know? All of the transitions in hydrogen, all of the photons in hydrogen that are produced here are also produced in the unknown gas. So therefore, hydrogen is present in the unknown gas. What about helium? Well, wait a second, though. Yeah. Wait a second. This one looks to be there, right? So wouldn't helium be there? No, they all have to be there. It's not just looking at one line and saying, oh, one line is there, so helium's there. No, all the lines from helium have to be there, and they're not. Only one of them is. What about sodium? We've got 2 lines from sodium at around 5.8. Oh, look, we do. We have that here. All of the lines from sodium are produced. So what's present in this unknown gas mixture? Hydrogen and sodium. Does that make sense? Yes.